Hello everyone, this is C241 Material Science. Serdar Göktepe speaking. In this video lecture, we will talk about thermoelasticity. Uh, this is a phenomenon that defines thermoelastic coupling. In other words, the effect of the temperature on the mechanical deformation of materials, and also the effect of the deformation on the temperature evolution within the material. This is typically observed as deviation from ideal linear elastic behavior of materials in the stress strain curves. So let's take a look at first what we will see, what happens if you deform a material at a higher rates of deformation. So in this stress strain diagram, you see essentially three classes of curves. The one that you see in the middle, the orange one, is the ideal elastic behavior. In this case, what you do is you deform the specimen at a rate which is slow enough so that the material's temperature essentially remains constant. These kind of deformations are referred to as isothermal deformations, where the temperature remains constant. Okay, but when you start to deform material at the rates that are drastically higher than the rates under which we observe isothermal behavior, we start to see some deviations from the ideal linear elastic behavior. For example, as shown by the black curve in the loading range and also a black curve in the unloading range. When you deform material at the rate which is extremely fast, that means you at the rate so the material doesn't have any time to exchange any thermal energy with the environment, the stress strain curve essentially looks pretty much like a dashed blue curve. And then we observe that the deviation is higher than compared to the black one. So let's take a closer look at what will happen if you deform material at the rate which is very high. So when you rapidly stretch a specimen, for example, energetic material like metal within the elastic range, along, for example, line from O to A, its temperature decreases. Okay, that means the material will deform less than as it was deformed slowly under isothermal conditions, because under isothermal conditions, remember, your deformation curve, stress strain curve would look pretty much like this orange one. But in the latter case, in the adiabatic case, where the loading rate is quite fast, you have the blue line from O to A. The reason is that the material essentially cools down when you stretch it. And then if you allow the specimen to remain under the load, which is denoted by line AB, constant load for a while, which is sufficient enough to let the specimen exchange thermal energy with the environment, it will actually warm up. Therefore, it will deform thermally from A to B. So therefore, in the loading branch from point O to B, we have two behaviors. One is the quick loading from O to A, and then where the material actually cools down, and when you keep the force constant, a material gets thermal energy from the environment, exchanges the energy, and heats up to the room temperature. Therefore, it expands. As you know from your elementary courses, materials expand when they are heated up and shrink as they are cooled down. So what happens if you unload the material along BC very quickly? The material will contract, but its temperature will increase. Okay, therefore it will contract less than if it was deformed at a slower rate or under isothermal condition. But then if you allow the specimen to actually stay at the constant load, for example, from C to O, it cools to the room temperature. Therefore, it shrinks further. So the loading line OA and unloading line BC are the paths that represent adiabatic processes. Adiabatic processes are the processes, as you will recall from your chemistry course, Chem 107, are the processes where the system doesn't exchange uh, any thermal energy with the environment. That means your system is insulated. In this case, the system is our specimen, in other words, the material. And in the loading line from O to A and in the unloading line from B to C, we deform the material such a high rate that material doesn't have time to exchange thermal energy with the environment. Therefore, along the line OA and in the unloading branch from B to C, we observe temperature changes. When the rate of the strain is positive, material cools down. When the rate of the strain is negative, in other words, when you compress the material towards its original position, material heats up. When you keep the force or stress, by the way, this is the stress axis. For some reason, stress label has been moved or removed. If you keep the stress constant, material along the line AB warms up to the room temperature. Just the opposite happens when you keep the stress constant along the line CO, where the forces or stress is constant, but the material exchanges thermal energy with the environment. Therefore, it cools down to room temperature, and therefore it shrinks and basically goes back to the original position. So this is what we refer to as adiabatic processes. That are the processes so fast that material doesn't have any time to change heat with the environment. So if the specimen is stretched at a rate which is slow enough, ideally slow enough, so material will have always time to exchange energy with the system. Therefore, we don't observe any with the environment. Sorry, therefore we don't observe any temperature changes. Therefore, in that case, what we obtain is the isothermal line, which represents the elastic behavior. And this behavior is referred to as isothermal behavior that corresponds to the response of the material under constant temperature, where we don't observe any temperature change because any heating that you would expect within the material will be dissipated to environment because you deform the material so slow that material will always have time to equilibrate itself thermally to achieve the environmental temperature or ambient temperature. So this is what we observed. And the reason why the materials cools down when they are, especially energetic materials, of course, the reason why the materials cools down when they are stretched and heats up when you compress them is at the atomic level is that when you stretch the materials, you bring the atoms apart from each other. The way how the thermal energy is stored in the microstructure atomic level is through the vibration of the atoms, and the way how the material's temperature changes at the atomic level is through the collision of the atoms. So that means when you stretch the material, since you bring the atoms more apart from each other, the probability that the atoms will collide each other will be less. Therefore, you expect temperature to decrease. This is for energetic materials. Just the opposite happens when you compress the materials, because when you compress the materials, you would bring the atoms closer to each other. Therefore, the probability that the atoms will essentially contact each other, collide with each other, will be higher. Therefore, temperature increases. And of course, this is also the mechanism through which heat is conducted at the microstructure. What happens if you look at the phenomenon of thermoelastic heating or thermoelastic cooling in compression and tension, respectively, at the macroscopic thermoelastic theory? So the equations you will probably see here will be relatively new, but you will grasp the concept if you think the things in terms of energy. As you know, the first law of thermodynamics says that energy of a system is preserved. In other words, change of the total energy of a system in time is equal to the total energy that is put into the system, supplied to the system. If you write such an equilibrium equation in terms of energy, you will end up with what we call the first law of thermodynamics. In this equation that you see here, on the left-hand side, we have the rate of the internal energy. And this rate of the internal energy is related to the mechanical working stress power, sigma times epsilon dot, where the dot denotes, used also here, denotes the derivative with respect to time. And moreover, besides the mechanical working stress power, we have a thermal power. So in thermomechanical theory, you can change the energetic state of a system through two different ways. You either deform the material, okay, or you supply thermal energy to the system. So thermal power represents the action of the rest of the system on the system of interest through the heat flux, for example, or represents the any heat generation inside the material. Under adiabatic conditions, where we insulate our system, in other words, specimen, thermal power is negligible. It is equal to zero. And this equation of first law of thermodynamics essentially boils down to ordinary differential equation that you see here, which says that uh, C times theta dot, where C is the specific heat. As you know, specific heat represents the amount of energy that is needed to increase a unit volume or unit mass of a material by single degrees Celsius, right? So specific heat times the rate of the temperature is equal to temperature times theta represents, of course, absolute temperature, temperature times derivative of the stress with respect to temperature times rate of the strain. So this is the adiabatic version of what we call the first law of thermodynamics, in other words, conservation of energy. So now, of course, in order to account for thermoelastic coupling, we need to extend Hooke's law, in other words, the constitutive equation that describes the relationship between the stress and strain towards thermoelasticity. So how do you do this? You do this in a simplest case, replace the strain that you see here, which is a mechanical strain that is the result of the deformation of the material, with the effective strain here, which is given by the strain due to the displacement minus the strain due to the temperature change. So the letter R, letter strain is called or referred to as thermal strain in this case. And thermal strain is defined as change in the temperature, which is current temperature theta minus the reference temperature theta 0 times alpha theta. And alpha theta stands for the thermal elongation coefficient. We have considered this coefficient when we discussed the atomic energy curves, remember, and there we have commented on that when the energy trough is deep and narrow. In other words, when the bond is stronger, the alpha theta is, in other words, the thermal elongation coefficient is smaller, right? So because it's going to be more difficult to expand or extend the material, elongate the material by changing the temperature. So this is the, if you like, the extension of the Hooke's law, isothermal law, towards thermoelastically coupled Hooke's law, where your stress is not only a function of the mechanical strain, but also dependent upon the thermal strain, which is given by the change in the temperature times the alpha theta that denotes the thermal elongation coefficient. So how do we define the thermal elongation coefficient? Sometimes in three-dimensional case, it is also referred to as thermal expansion coefficient. Through the following experiment. So assume that you have a bar which is fixed at left end. Initial temperature of this bar is denoted by theta 0 and initial length is denoted by L0. If you heat this bar uniformly so that you change its temperature from theta 0 to theta, where theta is greater than theta 0, you heat up the material and the length will change. And when you heat up a material, of course, the length will increase and current length is denoted by L. So the thermal elongation coefficient, alpha theta, is the coefficient that governs the elongation of this specimen. In other words, difference between the current length and the initial length, L minus L0, is given by thermal elongation coefficient alpha theta times change in the temperature times the initial length. In other words, if you divide the change in the length by the initial length, what you get is the strain, of course, and this strain is not due to the mechanical loading, but the temperature changes. Therefore, we refer to this strain thermal strain. And just the opposite happens when you cool down the material. In other words, if you have a bar, the same bar, that is initially, whose initial temperature is denoted by θ0. When you cool it down, it would shrink, of course. And in this case, thermal strain will be negative because theta is smaller than θ0. The specimen will reduce in length. All right. Since you don't restrain the motion of this bar during heating or cooling, no stresses will develop. What happens if you restrain the right end as well? In other words, if you set the mechanical strain to 0, if you go back to the extended Hooke's law in this expression, this means putting here a support so that the mechanical length is not allowed to change means setting epsilon to 0. And then this constitutive equation reduces or simplifies to this one. And what happens if you increase the temperature? When you increase the temperature, material wants to expand, but since you hold it on the right end, you don't allow it to expand. Therefore, intuitively expect that compressive stresses will develop. In other words, stresses that are compressing the bar in the longitudinal direction. And that is theoretically represented by this formula. When you set the epsilon to 0, you end up with the stress, which is proportional to a change in the temperature. You can imagine this also through the superposition. For example, in the first place, you can assume that the right end is free. You let the bar elongate under heating to a length, let's say L. And in order to bring to the bar to the initial position, you of course need to apply a compressive force to bring it to the original length L0. Therefore, through the superposition principle, you can also intuitively understand that the stresses that will develop upon heating when the bar is restrained at both ends will be compressive. When you cool it down, of course, the stress will be positive. Therefore, tensile stresses will develop because bar will tend to shrink. But since you don't allow it to shrink, you have to pull it, and that to let it just to force it stay in the at the same line. So you got to apply tensile stress that is represented in this expression. This is positive because theta is smaller than θ0 in this case. Therefore, two negative signs makes the stress positive. So far, what we have seen is the effect of the temperature on the mechanical response. But what we like to also explain is to what we have seen in the first slides. In other words, what happens under adiabatic conditions if I deform the bar by deforming the bar at the very fast rate of the deformation in tension and compression to see whether this constitutive relationship, simple extension of the Hooke's law can explain thermoelastic cooling and heating, respectively, in tension and compression. All right. So what you need to do is then you need to remember the adiabatic version of the first law. We had this in the first place. And then plug in here the constitutive equation we had introduced, the simplest constitutive equation we had introduced for thermoelastic material, where the strain is replaced, mechanical strain is replaced by the mechanical strain minus the thermal strain. Therefore, stress is not only dependent upon the mechanical strain, but also the temperature. Therefore, then you can take this derivative because your stress is a function of temperature. When you take this derivative for this constitutive equation, and plugging into the first law, you obtain this. This equation actually says, in the first place, what we have observed in the initial slides. So heat capacity is always positive, right? And theta is absolute temperature that is always greater than 0. Young's modulus is positive. Thermal expansion coefficient is also positive. That means all these material properties are positive and absolute temperature is positive. Therefore, this equation says us that the sign of the rate of the temperature is just the opposite of the sign of the rate of the strain. This is obviously explains what we observed. That means if you compress the material where the rate of the strain is negative, the rate of the temperature will be positive. In other words, temperature will increase. Or if you extend the specimen at a positive strain rate, then the rate of the temperature will be negative. Therefore, temperature will tend to decrease. So mathematically, you can actually show it very well. So you can solve this differential equation analytically. In other words, if you divide the both parts by theta and observe that theta dot over theta is the nothing but the rate of the logarithm of theta, and when you integrate the epsilon dot over the time from t0 to t, where t0 is the initial time, you obtain change in the strain. And take the exponential of the both parts. Of course, before you do it, you divide by c, and multiply with the theta 0, you obtain theta as theta equals theta 0 times exponential this expression. So when you draw this expression, in other words, theta versus epsilon diagram, your initial point is epsilon 0 and theta 0. That is the initial strain value corresponding to the initial temperature, theta 0. Generally, initial strain is 0 because we use starter deformation in general from undeformed state. But if you want to account for misfits or purposely introduced pre-deformation in the material, you can account for that through epsilon 0 value not being different from 0. So when you draw this function, as it is indicated in this exponential curve, when you increase the strain, material will cool down, all right? So temperature will decrease. If you compress the material, on the other hand, it will warm up. Okay, this is what you observe. So in real life, of course, deformations are not adiabatic, right? So actually, not adiabatic or not isothermal either. There will always be some heat exchange. Therefore, the real behavior is somewhere in the middle. Therefore, you don't observe generally what you see here is a straight line that represents the isothermal behavior, or the dashed blue line that represents the adiabatic response. But in reality, what you have is this kind of hysteresis loop, and the area in this hysteresis loop that is in this reddish color represents the energy lost, thermoelastic damping effect. Okay, so this is actually negligible for metals, but when it comes to polymeric materials, that is more pronounced. And heating and cooling of a material is a result of its deformation called the thermoelastic effect. This is also referred to as retarded elasticity. Retarded means, as you know, delayed. So if you consider, for example, the adiabatic curve compared to the isothermal curve, latter being the ideal elastic behavior, blue line is the retarded response of the isothermal curve, because when you wait at this point, remember at point A in the original diagram, at the constant stress value, it approaches to isothermal case through the heat exchange. Therefore, you observe some convergence to the ideal elastic behavior, but with a delay. That's why probably people call this phenomenon retarded elasticity as well. But in general, it is better to call it thermoelastic coupling or thermoelastic effect. So in the elastic analysis of metals, it is assumed that this elastic strain is a function of stress only. When it comes to elasticity at small deformations, we do it in general. But This is not strictly true because, as you see, depending upon the rate of the loading, you observe some deviations. Therefore, stress strain response is also a function of the time. This is very small in metals, but in polymers, this is more pronounced, and it becomes much more pronounced if you increase the loading rates and also the load levels. And then this is generally referred to as viscoelastic response. That is going to be the topic of the chapter that we will cover in week number 9, I believe. So in general, this kind of time dependence, defining the deviations, time dependent deviations from the elastic response, are referred to as unelasticity. And thermoelastic effect or retarded elasticity are some examples, aspects of unelasticity. So this is pretty much all I like to say about thermoelastic coupling. Next week, we will be talking about plasticity. I talk to you later. Bye-bye.